The Unseen Giant, ASML, the Geopolitics of Light and the Architecture of the Digital Age. The Silicon Singularity. In the grand tapestry of human technological evolution, few threads are as critical, yet as invisible to the naked eye, as the transistor. It is the fundamental neuron of the digital brain, the binary switch that underpins the modern world. From the hyperscale data centers training large language models to the guidance systems of ballistic missiles, and from the smartphone in a teenager's pocket to the ECU controlling an electric vehicle's braking system, the integrated circuit is the bedrock of contemporary civilization. The global semiconductor industry, a colossus valued at over $500 billion, acts as the nervous system of the global economy. Yet, this entire sprawling, complex, and indispensable industry rests precariously on a singular choke point. It depends on the capabilities of one company, located in a quiet provincial town in the southern Netherlands. That company is ASML Holding N.V. To call ASML a monopoly is an understatement that fails to capture the nuance of its position. It is the sole guardian of the gate to the future. ASML does not merely manufacture equipment, it orchestrates the boundaries of physics. It is the only company on Earth capable of building extreme ultraviolet lithography machines, devices of such staggering complexity that they have been termed the most complex machines ever built by humanity. Without ASML, there is no 5-nanometer chip. Without 5-nanometer chips, there is no advanced artificial intelligence, no next-generation military hardware, and no continuation of Moore's law. This report delves into the untold story of this unseen giant, tracing its journey from a leaky shed in Eindhoven to the center of a global geopolitical storm, and unpacking the complex magic of photolithography that allows it to print circuits on an atomic scale. The genesis of a titan. The origins of ASML are humble, almost deceptively so, given its current status as Europe's most valuable technology firm. The company was born in 1984, not amidst the fanfare of a Silicon Valley IPO, but in the quiet industrial corridors of Eindhoven. It was established as a joint venture between the Dutch electronics conglomerate Philips and ASM International, a semiconductor equipment manufacturer. At the time, the lithography market was a crowded and fierce arena. American giants like Perkin-Elmer and GCA Corporation held the technological crown, while Japanese conglomerates Nikon and Canon were rapidly ascending, fueled by massive capital and efficient manufacturing prowess. ASML was the underdog, entering the race late with technology that was viewed with skepticism. The initial team consisted of just 31 employees who set up shop in a temporary facility next to the Philips NatLab physics laboratory. Industry lore often refers to this first headquarters as the leaky shed, a literal description of the working conditions, where buckets were sometimes needed to catch rainwater, a stark contrast to the ultra-clean rooms of today. The first decade, often referred to as the lean years, was characterized by a perpetual struggle for survival. The semiconductor industry is notoriously cyclical, prone to boom and bust cycles that can wipe out capital-intensive equipment manufacturers. ASML had no financial cushion. It survived largely on the strategic patience of its parent companies and the sheer grit of its engineers. This era forged a unique corporate culture: firefighter engineering. Lacking the resources to perfect every subsystem in the lab, engineers often had to fix machines on site at customer fabs, improvising solutions to keep the lines running. This engendered a deep service-oriented DNA that prioritized customer uptime above all else. a trait that would later become a key differentiator against the more rigid Japanese competitors. By the late 1980s, ASML was still a minor player, but the seeds of its future dominance were being sown in the R&D department. The turning point arrived in 1991 with the launch of the PAS 5500 platform. Before the PAS 5500, lithography tools were typically monolithic. If a chip manufacturer wanted to upgrade their resolution or throughput, they often had to scrap the old machine and buy a new one. This was inefficient and costly. Under the technical leadership of Martin van den Brink, a young engineer who would eventually rise to become the company's president and CTO, ASML introduced a revolutionary modular architecture. The PAS 5500 was designed like a Lego set for high-tech manufacturing. It allowed for incremental upgrades. A customer could swap out the lens column or the wafer stage without replacing the entire chassis. This dramatically reduced the total cost of ownership, or TCO, for chip makers. They could extend the life of their capital equipment, producing multiple generations of chips on the same baseline platform. The system utilized a unique alignment strategy that proved superior in overlay accuracy, the ability to align the new layer of a chip perfectly with the layer beneath it. This platform was the catalyst for ASML's first major strategic victory, winning the trust of Taiwan Semiconductor Manufacturing Company, or TSMC. In the early 1990s, TSMC was a young foundry trying to establish itself. ASML's willingness to customize the PAS 5500 to TSMC's specific requirements created a symbiotic bond. As TSMC grew to become the world's largest foundry, ASML grew with it, riding the wave of the fabless revolution. By the turn of the millennium, the lithography wars had narrowed to a three-way fight: Nikon, Canon, and ASML. The Japanese firms were the incumbents, but ASML was about to play its trump card, the TwinScan platform, introduced in 2000. Traditional step and scan systems performed two critical functions: measuring the wafer surface, metrology, and exposing the wafer to light, lithography, sequentially on a single stage. This meant the expensive lens sat idle while the machine measured the wafer. The TwinScan architecture introduced two simultaneous stages. Measurement station. While one wafer is being exposed, a second wafer is on a separate stage being mapped. The machine creates a precise 3D topographical map of the silicon surface, detecting nanometer-scale irregularities. Exposure station. Once mapped, the stages swap. The exposure lens can now print the circuit pattern at high speed, adjusting its focus in real time based on the 3D map created seconds earlier. This parallel processing architecture yielded a massive increase in productivity, or wafers per hour, and accuracy. It allowed ASML to offer higher throughput than Nikon or Canon, a critical metric for high-volume manufacturers like Intel and Samsung. By 2002, thanks to TwinScan and the acquisition of Silicon Valley Group, or SVG, ASML became the market leader in lithography. The physics of the impossible. Immersion and EUV. The history of lithography is a history of shrinking wavelengths. To print smaller features, one must use light with a shorter wavelength. The industry progressed from the visible spectrum to ultraviolet and then to deep ultraviolet, DUV, using krypton fluoride and argon fluoride lasers. In the early 2000s, the industry hit a brick wall at 193 nanometers. The next logical step was supposed to be 157 nanometers F2 laser lithography. However, the optics for 157 nanometers, which required calcium fluoride lenses, were proving brittle, expensive, and optically flawed due to intrinsic birefringence. While Nikon and Canon poured resources into trying to make 157 nanometers work, ASML took a different path. Influenced by researcher Bernjang Lin at TSMC, they bet the company on immersion lithography. Instead of filling the gap between the lens and the wafer with air, fill it with ultra-pure water. Water has a refractive index of 1.44 compared to 1.0 for air. According to the laws of optics, increasing the refractive index, N, increases the numerical aperture of the system. A higher NA allows for tighter focusing of light, enabling smaller features to be printed using the same 193 nanometer light source. The result was the TwinScan XT1950i, a machine that became the workhorse of the industry for over a decade. It allowed chipmakers to push down to the 38 nanometer node and beyond, effectively killing the 157 nanometer roadmap and leaving competitors who had invested in it stranded with obsolete technology. ASML's market share surged to over 80% in the high-end segment. If immersion lithography was an evolutionary step, extreme ultraviolet, EUV, was a quantum leap. It represents the most difficult engineering challenge in the history of electronics. The goal was to jump from 193 nanometers all the way down to 13.5 nanometers. This is not just bluer light. At 13.5 nanometers, light behaves more like X-rays. It is ionizing radiation that is absorbed by virtually all matter. It cannot travel through air. It must travel through a vacuum. It cannot be focused by glass lenses. It must be reflected by mirrors. The development of EUV began not in the Netherlands, but in the United States. In 1997, Intel and the U.S. Department of Energy formed the EUV LLC, a consortium involving Lawrence Livermore, Sandia, and Lawrence Berkeley National Laboratories. The goal was to prove that soft X-ray projection lithography was possible. Crucially, the U.S. government had to decide who would commercialize this technology. Japan's dominance in the 1980s semiconductor market had spooked Washington. Although Nikon and Canon were technically capable, the U.S. effectively barred them from the consortium to prevent Japanese dominance of the next technological era. ASML, however, was seen as a safe partner, a NATO ally with a smaller footprint. They were invited to join the EUV LLC, provided they established a manufacturing base in the U.S. and acquired the American firm Silicon Valley Group Lithography, SVGL. This decision, made in the late 90s, effectively handed the monopoly on the future of computing to ASML. The heart of an EUV machine is the source, a device that generates the 13.5 nanometer light. It operates at the very edge of physics, creating conditions similar to the interior of a star. ASML's source, developed by its subsidiary Cymer, uses molten tin. A generator shoots microscopic droplets of tin, roughly 25 microns in diameter, into a vacuum chamber. These droplets are fired at a rate of 50,000 per second, or 50 kilohertz. They travel at speeds exceeding 70 meters per second, approximately 160 miles per hour. Hitting a moving microscopic target with a laser is hard. Doing it 50,000 times a second with perfect consistency is nearly impossible. ASML uses a pre-pulse and main pulse strategy. A low-energy laser shot hits the tin droplet. This does not vaporize it. Instead, it imparts momentum that flattens the spherical droplet into a pancake-shaped disc. This increases the surface area and prepares the target. Microseconds later, a high-power carbon dioxide laser, developed by German partner Trumpf, strikes the flattened disc.
This laser is powerful enough to cut through steel, 30 kilowatts input power. The tin is instantly vaporized into a plasma with a temperature of roughly 220,000 degrees Celsius. For context, this is nearly 40 times hotter than the surface of the sun. As the highly ionized tin atoms decay to a lower energy state, they emit a photon. Crucially, they emit a spike of radiation at exactly 13.5 nanometers. This process is incredibly inefficient. The conversion efficiency from laser power to EUV light is less than 5 to 6%. To generate the required 250 watts of EUV light at the intermediate focus needed for high-volume manufacturing, the drive laser must pump in tens of kilowatts of energy. Dealing with the waste heat and the debris from this violent explosion was the primary reason EUV was delayed for over a decade. Since glass absorbs 13.5 nanometer light, ASML had to abandon refractive lenses. Instead, EUV machines use a system of highly complex mirrors to guide the light to the wafer. These are not bathroom mirrors, they are Bragg reflectors. Manufactured by Carl Zeiss SMT in Germany, these mirrors consist of a substrate coated with up to 100 alternating layers of molybdenum, Mo, and silicon, Si. The thickness of each layer is controlled to atomic precision, roughly 3 to 4 nanometers per layer, to ensure constructive interference of the light waves. The flatness specifications are mind-boggling. ASML and Zeiss engineers state that if you were to scale one of these mirrors up to the size of the Earth, the largest bump or valley on the surface would be smaller than a human hair, or roughly the size of a golf ball, depending on the specific mirror generation. The sensors and actuators that position these mirrors must be accurate enough to hit a golf ball on the moon with a laser. The entire optical train must exist in a high vacuum. However, the tin plasma explosion creates high-energy ions and debris that would normally coat and destroy the collector mirrors within minutes. To solve this, ASML flows hydrogen gas through the source vessel. The gas acts as a physical buffer, slowing down the tin ions before they hit the optics. Under the intense EUV radiation, the hydrogen gas turns into hydrogen radicals. These radicals chemically react with the tin deposited on the mirrors to form stauanine, a gaseous compound that can be pumped out of the chamber. This continuous self-cleaning chemical reaction is the only reason EUV scanners can operate for weeks or months without maintenance. The architecture of monopoly, business, and ecosystem. The development of EUV was a financial black hole. Between roughly 2000 and 2012, ASML poured billions of euros into R&D with zero commercial revenue from the technology. By 2012, the financial strain was becoming untenable, and the light source power was still stuck at single-digit watts, far below the 250 watt needed for profitability. To survive, ASML launched a bold strategic initiative. They invited their 3 largest customers, Intel, TSMC, and Samsung, to become shareholders. Intel invested roughly 2.5 billion euros for a 15% stake. TSMC acquired a 5% stake. Samsung acquired a 3% stake. In total, this program raised nearly 4 billion euros in cash and secured R&D commitments for the next 5 years. This masterstroke did 2 things. It provided the capital needed to acquire Cymer, the light source maker, and it locked the world's biggest chip makers into the ASML ecosystem. They were no longer just customers, they were partners with a vested interest in ASML's success. This effectively closed the market to any potential competitors. ASML operates on a unique business model that differs significantly from the vertically integrated giants of the past. It describes itself as a system integrator. An EUV machine, such as the NXE 3400C or NXE 3600D, contains over 100,000 components. ASML manufactures only about 15% of the machine's value in-house. The rest comes from a sprawling supply chain centered in the Brainport Eindhoven region. ASML shares its long-term technology roadmap with its key suppliers like VDL for wafer handlers, ProDrive for electronics, and Trumpf for lasers. This allows suppliers to invest in the necessary tooling and factories years in advance, knowing that orders will come. This open innovation model creates a resilient, interdependent web. A cornerstone of this ecosystem is the Inter-University Microelectronics Center, IMEC, in Belgium. IMEC acts as a pre-competitive research hub, where ASML, ZEISS, and chip makers collaborate to test prototypes, like the High-NA lab, and develop the photoresists and masks needed for future nodes. While ASML prefers partnership, it will acquire companies if they represent a critical bottleneck. When Cymer, based in San Diego, struggled to deliver a powerful enough EUV light source, threatening the entire EUV program, ASML acquired the company for $2.5 billion to take direct control of the source development. The relationship with ZEISS is symbiotic. While ASML does not own ZEISS, which is a foundation-owned company, it acquired a 24.9% stake in ZEISS SMT, the semiconductor division, in 2016 for €1 billion. This capital injection was specifically to fund the development of the massive mirrors required for High-NA. Manufacturing and logistics, moving mountains. The assembly of an EUV machine takes place in Veldhoven, in some of the most advanced clean rooms in the world. The environment is controlled to eliminate particles that could land on a reticle or mirror. A single speck of dust in an EUV system can cause a killer defect that ruins every chip on a wafer. Once built and tested, delivering the machine is a logistical operation rivaling military deployments. An EUV scanner weighs approximately 180 tons. It is disassembled into modules and packed into 40 specialized freight containers. It requires 3 to 4 Boeing 747 cargo planes to transport a single system to a customer in Taiwan, Korea, or the US. Upon landing, a convoy of roughly 20 trucks is needed to move the components to the fab. Once on site, a team of ASML engineers spends months reassembling and calibrating the machine. ASML maintains a permanent presence inside its customers' fabs, with thousands of service engineers ensuring the machines maintain uptime, availability of over 90–95%. To sustain this innovation, ASML recruits aggressively from the world's top universities. It has a massive intake of PhDs in physics, optics, mechatronics, and materials science. The company fosters a culture of challenge, where engineers are encouraged to debate solutions regardless of hierarchy. This intellectual density is ASML's ultimate moat. Even if a competitor stole the blueprints, they would lack the tacit knowledge of the 40,000-plus employees who know how to make the machine. The geopolitical choke point, the chip war. By 2018, the world woke up to the reality that ASML was not just a company, but a strategic geopolitical asset. As tensions between the United States and China escalated, semiconductor manufacturing became the central front of the chip war. The US government identified advanced lithography as the choke point to halt China's military modernization. Because ASML's machines use US origin technology, specifically from the Cymer acquisition and the EUV LLC patents, they are subject to US export controls under the Foreign Direct Product Rule, or FDPR. Under pressure from the Trump administration, the Dutch government revoked ASML's export license for EUV machines to China. This effectively capped China's domestic chip industry at the 7-nanometer node, which can be achieved, albeit inefficiently, with older DUV machines, and prevented them from efficiently producing 5-nanometer or 3-nanometer chips needed for advanced AI and mobile processors. In 2023, the Biden administration pushed for tighter controls. The restrictions were expanded to include advanced deep ultraviolet immersion systems, specifically the NXT2000i and subsequent models. These are the workhorse machines used for 7-nanometer to 40-nanometer production. The goal is to widen the gap between Western and Chinese capabilities. This puts ASML in a precarious position. China has historically been one of its largest markets, accounting for 30 to 40% of system sales in recent years, as Chinese fabs engaged in panic buying of older tools before bans took effect. ASML warned that the new export rules would affect 10 to 15% of its China sales in 2024. By cutting off China, the West is forcing Beijing to invest billions into its own lithography supply chain via companies like SMEE. While currently decades behind, the containment strategy risks creating a fully independent competitor in the long run.
The future, high NA and beyond. ASML is not resting on its monopoly. It is currently rolling out the next generation of lithography, designed to keep Moore's Law alive through the 2030s. Current EUV machines have a numerical aperture, or NA, of 0.33. The new platform, the TwinScan EXE, starting with the EXE 5000, features an NA of 0.55. A higher NA allows for better resolution. This will enable chip makers to print features smaller than 2 nanometers without using complex and expensive double patterning techniques. To achieve this NA without making the machine impossibly large, Zeiss developed anamorphic optics. These mirrors have different magnification factors in the X and Y directions, 4x versus 8x. This requires the image on the mask to be stitched together on the wafer, adding a new layer of complexity to the process. These machines are priced at approximately 350 to 400 million euros each. Intel was the first customer to receive a pilot high-NA system in Oregon in late 2023, betting on this technology to regain its manufacturing lead over TSMC. Is there a limit? Martin van den Brink has discussed the theoretical possibility of Hyper-NA, which would likely be the final generation of optical lithography, before the wavelength of light simply becomes too difficult to manipulate, or the cost becomes prohibitive. Recent density records achieved in the joint ASML-IMEC lab suggest that high NA is performing well, printing lines as thin as 8 nanometers. However, the economic viability of these machines, whether the cost per transistor continues to fall, remains the ultimate test. ASML's journey from a leaky shed to the unseen giant of the global economy is a testament to the power of long-term vision and collaborative innovation. By betting the company on unproven technologies like Immersion and EUV, and by orchestrating a global ecosystem of suppliers and customers, ASML has built a moat that is currently insurmountable. As the world pivots towards the era of artificial intelligence, the importance of ASML only grows. The training of massive neural networks requires the most advanced GPUs, which can only be manufactured using ASML's EUV tools. In this sense, the future of human intelligence is being forged in a vacuum chamber in Veldhoven, one tin droplet at a time.
The company has become the ultimate gatekeeper, a singular node upon which the entire digital superstructure of the 21st century rests.
The Lithography Singularity, an exhaustive analysis of ASML's ecosystem, material physics, and computational infrastructure. The Convergence of physics and logistics. The contemporary semiconductor industry, and by extension the entire global digital economy, rests precariously on a single technological pivot point: the extreme ultraviolet lithography systems manufactured by ASML Holding NV. These machines are not merely industrial tools, they are the most complex machines ever constructed by humanity, representing a singularity where theoretical physics, material science, advanced computation, and global logistics converge. The production of a leading-edge microchip, now approaching the 2-nanometer node, requires a level of precision that defies intuition, relying on a supply chain that functions less like a series of vendors and more like a distributed, planetary-scale research institute. This part provides an exhaustive technical and operational analysis of the ASML ecosystem. It moves beyond the surface-level understanding of chip printing to explore the subatomic material engineering of Zeiss mirrors, the computational leviathan required to calculate inverse lithography patterns, the metrological feedback loops that operate at the picometer scale, and the geopolitical and logistical intricate dance required to bring these systems online. The analysis reveals that ASML's monopoly is not born solely of patent protection or capital investment, but of a decades-long accumulation of tacit knowledge dispersed across thousands of specialized partners. From the chaotic plasma physics of tin droplet vaporization to the deterministic execution of millions of lines of embedded code, the ASML lithography scanner is the ultimate validation of Moore's law, pushing the boundaries of what is thermodynamically and economically possible. The material physics of extreme ultraviolet light. The transition from deep ultraviolet lithography, utilizing 193 nanometer light, to extreme ultraviolet lithography, utilizing 13.5 nanometer light, was not an evolutionary step. It was a fundamental disruption of optical physics. Light at 13.5 nanometers behaves less like a wave and more like a high-energy particle, and crucially, it is absorbed by virtually all known matter, including air and standard glass lenses. This physical reality necessitated the abandonment of refractive optics, lenses that bend light, in favor of an all-reflective system, a technological pivot that required the reinvention of material science at the atomic level. The selection of 13.5 nanometers as the wavelength for EUV lithography was not arbitrary. It was dictated by the specific atomic transitions of tin. To generate EUV light, a plasma must be created that emits photons in this specific spectral band. The industry settled on laser-pulsed tin plasma because tin ions, specifically in the ionic states from SNIX to SNXIV, exhibit strong photon emission spectral peaks around 13.5 nanometers. These emissions arise from specific electronic transitions. The 4p6 4dn to 4p5 4dn plus 1 plus 4dn minus 1 4f transitions within the highly ionized tin atoms. Creating these ions requires stripping away between 8 and 13 electrons from a tin atom, a violent process that demands an environment characterized by extreme energy density. The plasma must reach temperatures exceeding hundreds of thousands of degrees Celsius, mimicking the conditions found in stellar atmospheres to achieve the necessary ionization states. This reliance on tin plasma introduces a host of material challenges. The plasma is generated by firing a high-power CO2 laser at a microscopic droplet of molten tin, approximately 30 microns in diameter,
traveling at speeds up to 70 meters per second through a vacuum chamber. The laser must strike the droplet twice, a pre-pulse to flatten the spherical droplet into a pancake shape to maximize surface area, and a main pulse to vaporize it into plasma. This sequence occurs 50,000 times per second. Because 13.5 nanometer light is ionizing radiation, it interacts strongly with matter. It strips electrons from atoms, meaning it is absorbed by air, nitrogen and oxygen, almost instantly. This necessitates that the entire optical path, from the source to the wafer, be maintained under high vacuum. This vacuum requirement ripples through every aspect of the machine's design. Materials used in the construction of the stage, the cable harnesses, and the sensors must be vacuum compatible, meaning they must not outgas. Outgassing, the release of trapped gas molecules from a material, would not only compromise the vacuum level, but could also deposit contaminants on the mirrors. Carbon contamination is a particular enemy. EUV light can crack carbon-containing molecules, depositing a layer of graphite on the mirrors that absorbs light and reduces throughput. ASML systems therefore include active cleaning modules that use hydrogen radicals to scrub carbon deposits from the mirror surfaces during operation. The optical masterpiece, atomic engineering of mirrors. In the absence of lenses, the EUV scanner relies entirely on mirrors. However, at 13.5 nanometers, even the most reflective surfaces known to man, such as polished gold or iridium, have negligible reflectivity at normal incidence. To reflect EUV light, ASML and Zeiss had to engineer a new class of optical element, the distributed Bragg reflector. A Bragg mirror operates on the principle of constructive interference rather than simple metallic reflection. It consists of a stack of alternating material layers, specifically molybdenum and silicon. Silicon is chosen because it is relatively transparent to 13.5 nanometer light, though still absorptive compared to glass in visible light, while molybdenum acts as a scattering layer. The mirror comprises roughly 40 to 50 pairs of these layers, 80 to 100 layers total. The thickness of each layer is engineered to be exactly 1/4 of the wavelength of the light, adjusted for the angle of incidence and the refractive index of the materials. When EUV photons strike the stack, a small percentage reflects off each MOSI interface. Because of the precise spacing, these small reflections align in phase, combining to form a strong, coherent reflected beam. The manufacturing tolerance for these layers is unforgiving. If the thickness varies by even a fraction of a nanometer, the interference becomes destructive and reflectivity plummets. Even with perfect manufacturing, the theoretical maximum reflectivity of a MOSI mirror is approximately 70%. The remaining 30% of the energy is absorbed by the mirror structure. In a system with an optical train containing 10 or more mirrors, the total transmission is 0.7 to the 10th, or roughly 2.8%. This enormous loss explains why the source power must be so high, kilowatts, to deliver just milliwatts of exposure energy to the wafer. The surface figure precision required for EUV optics is often illustrated with a staggering analogy. If one of these mirrors were enlarged to the size of Germany, the tallest mountain or deepest valley on its surface would be no more than 0.1 millimeters, 100 micrometers high. This level of smoothness, defined in the picometer range, RMS less than 50 pm, is critical because any surface irregularity larger than a fraction of the wavelength would cause phase errors, destroying the image contrast required to print features as small as 8 nanometers. Achieving this atomic flatness requires a manufacturing process that transcends traditional mechanical polishing. The process begins with high-precision grinding and polishing of the substrate, usually a zero-expansion glass ceramic material like Zeradur. Zeradur is essential because it maintains its shape even when subjected to thermal gradients, a critical property given the heat load from the absorbed EUV light. However, mechanical polishing leaves residual errors and subsurface damage. To correct these, Zeiss employs ion beam figuring. In the IBF process, a focused beam of argon or xenon ions is raster scanned across the mirror's surface. By controlling the dwell time of the ion beam at specific coordinates, material is removed atom by atom. This subtractive manufacturing technique allows for the correction of figure errors on the nanometer scale without introducing new mechanical stresses or scratches. The metrology required just to measure these mirrors during fabrication is a technological marvel in itself. Zeiss had to develop custom interferometers operating in high vacuum environments to detect deviations that are invisible to conventional instruments. These interferometers must be isolated from seismic vibrations and thermal fluctuations, often requiring massive, isolated concrete foundations for the measurement tools themselves. The absorption of EUV light by the mirrors introduces a secondary challenge: heat. Even with ultra-low expansion materials, the thermal energy deposited by the 30% absorption rate can induce localized deformations known as thermal lensing, which would distort the wavefront and ruin the exposure. To combat this, ASML and Zeiss have integrated active thermal control systems into the optical column. These systems utilize a combination of internal microchannels for water cooling and active heating elements. Counterintuitively, heaters are used to maintain the mirror at a uniform, elevated temperature where the coefficient of thermal expansion for the substrate is exactly zero, the zero crossing temperature. By carefully balancing the heat load from the EUV light with the active heaters and cooling channels, the system maintains the mirror's shape stability in the millikelvin range. Furthermore, the mirrors are mounted on active actuators, capable of adjusting their position and orientation in 6 degrees of freedom with nanometer precision, compensating for any residual drift or vibration in real time. The introduction of high numerical aperture EUV, specifically the EXE5000 and subsequent EXE5200 systems, necessitated a radical redesign of the optical train. Increasing the numerical aperture, NA, from 0.33 to 0.55 allows for higher resolution, effectively shrinking the Rayleigh diffraction limit, the fundamental barrier to printing smaller features. However, increasing the NA implies capturing light at steeper angles. In a traditional spherical optical design, this would result in incident angles on the mask, or reticle, that are too steep, causing shadowing effects, where the 3D absorber structures on the mask block the reflected light. This mask 3D effect would reduce contrast and cause pattern placement errors. To solve this, ASML and Zeiss introduced anamorphic optics. Unlike standard lenses or mirrors which magnify or demagnify an image equally in all directions, isomorphic, anamorphic optics have different magnification factors for the X and Y axes. The high NA system uses 4x magnification in the scanning direction, X, and 8x magnification in the slit direction, Y. This allows the system to maintain a manageable incident angle at the mask while achieving the high NA required at the wafer. This design choice has profound implications for the rest of the system. It requires the use of half fields on the mask. A standard reticle, or mask, is a 6-inch square. In 0.33 NA systems, the scanner exposes a field of 26 mm by 33 mm on the wafer. Due to the 8x magnification in Y for high NA, the field size on the wafer is halved to 26 mm by 16.5 mm. This necessitates stitching, printing 2 half fields next to each other to create a full die. It also demands significantly faster wafer and reticle stages to maintain throughput, as the scanner must perform more passes to cover the same wafer area. The EXE5000's reticle stage, for instance, must accelerate at a staggering 32G, 4 times faster than previous generations, to keep up with the optical requirements.
The metrology feedback loop, precision beyond lithography. A common misconception is that ASML's machines are merely printers. In reality, they are part of a cyber-physical system where measurement, metrology, is as critical as exposure. As feature sizes shrink below 10 nanometers, the margin for error effectively vanishes. A drift of a few nanometers in overlay, the alignment of one layer to the next, or critical dimension, CD, can render a chip useless. To ensure yield, ASML has developed a holistic lithography approach, tightly integrating metrology data into the scanner's control loop. For high-speed, inline metrology, ASML utilizes its YieldStar systems. Traditional microscopes, such as critical dimension scanning electron microscopes, CDCEMs, are excellent for imaging, but slow. To measure thousands of points on a wafer quickly enough to provide real-time feedback, ASML turned to scatterometry. YieldStar operates on the principle of diffraction. It shines a broadband light beam ranging from UV to near IR onto a specific target, a diffraction grating printed in the scribe lines, the spaces between chips, of the wafer. The way the light scatters and diffracts off this grating provides a fingerprint of the structure. By analyzing the diffraction pattern, the intensity and phase of the scattered light orders, software algorithms can reconstruct the physical profile of the printed structure with sub-nanometer accuracy. This process relies on solving the inverse electromagnetic problem using rigorous coupled wave analysis, or RCWA. The system compares the measured diffraction signature against a library of simulated signatures corresponding to different geometric profiles, such as line width, sidewall angle, and height. This allows YieldStar to measure overlay, focus, and dose errors across the wafer at high speed. Crucially, this data is not just for post-mortem analysis. It is fed back to the lithography scanner in a real-time control loop. If YieldStar detects that the overlay is drifting due to process variations, such as thermal expansion of the wafer or subtle lens heating, it calculates a high-order correction set that the scanner applies to the very next wafer or even the next field on the same wafer. While optical scatterometry is fast, it relies on models and specific targets. It cannot see stochastic defects, random failures where a line breaks or two lines bridge together due to photon shot noise or resist inhomogeneities. To see what is actually happening inside the dense circuit patterns, ASML relies on electron beam inspection, a capability secured through the acquisition of Hermes Microvision, HMI. E-beam systems, such as the HMI EP5, use a focused beam of electrons to scan the wafer surface. Electrons have a much shorter wavelength than photons, allowing for resolution down to 1 nanometer. The beam interacts with the sample, generating secondary electrons, SE, and backscattered electrons, BSE, that are detected to form an image. This provides the ground truth of the patterning process. E-beam metrology is historically slow, making it suitable for R&D, but difficult for high-volume manufacturing, HVM. A single beam scanning a 300mm wafer would take days. However, ASML has integrated HMI systems into the holistic loop by using them to calibrate the optical models. The pattern fidelity control paradigm uses the massive data from E-beam inspection to verify hotspots, areas of the chip design known to be difficult to print. Furthermore, ASML is advancing multi-beam E-beam technology, eScan 1000 and 1100, which uses multiple electron beams in parallel to drastically increase throughput, allowing for more comprehensive defect inspection in production environments.
The integration of yield star and HMI data creates a measured representation of the wafer that complements the modeled representation from computational lithography. The scanner itself is equipped with thousands of sensors, measuring temperature, pressure, vibration, and light intensity. This sensor fusion allows the machine to adjust soft knobs, software-definable parameters, to compensate for physical deviations. For example, if the metrology data indicates a systematic overlay error in the shape of a saddle across the wafer, a common thermal signature caused by wafer processing steps like annealing, the scanner's wafer stage can actuate to trace a compensatory path during the exposure scan. The stage effectively wiggles the wafer during the scan to match the distortion of the previous layer. This capability to dynamically distort the exposure grid to match the distorted wafer is essential for multi-patterning, where a wafer might be exposed 4 times to create a single layer, requiring overlay accuracy of just a few nanometers. Dedicated chuck overlay, less than 1.4 nanometers. The computational brain, software stacks, and inverse lithography. The physical hardware of an EUV scanner is controlled by a software stack of immense complexity, comprising millions of lines of code. However, the true computational heavy lifting occurs before the scanner even turns on, during the optical proximity correction, or OPC, and mask synthesis phase. As lithography moved into the sub-wavelength regime, where the features being printed are smaller than the light used to print them, the image projected onto the wafer ceased to look like the pattern on the mask. Diffraction causes corners to round off and lines to blur. To correct for these optical distortions, chip makers employ computational lithography. The layout of the chip is not sent directly to the mask writer. Instead, it is processed through algorithms that simulate the physics of the lithographic process and essentially reverse engineer the mask pattern required to produce the desired on-wafer image. This often results in mask shapes that look nothing like the final circuit. A simple rectangular transistor gate might be represented on the mask as a dog bone shape with serifs and independent assist features, or SRAFs, that don't print themselves, but steer the light to sharpen the main feature. ASML's acquisition of Bryon Technologies gave it control of the Tachyon platform, a dominant system for this computational task. Tachyon uses physics-based models to simulate the lithographic exposure. As nodes have shrunk, the complexity of these models has exploded. For high-NA EUV, simple rule-based OPC is insufficient. The industry is moving toward inverse lithography technology, or ILT, which treats the mask optimization as a mathematical inverse problem. In ILT, the entire mask is treated as a grid of pixels, and the algorithm optimizes every pixel to maximize the image contrast on the wafer. This creates curvilinear masks, complex organic-looking patterns that are mathematically optimal but computationally incredibly expensive to generate. These curvilinear masks are difficult to write with traditional variable-shaped beam mask writers, but the advent of multi-beam mask writers from IMS Nanofabrication, recently acquired by Intel and others, has made them feasible. The move to ILT and high-NA EUV has caused a crisis in computational cost. Generating a full chip mask using ILT can require weeks of processing time on massive CPU clusters, consuming tens of billions of CPU hours annually across the industry. A single mask set for a leading-edge node can contain 80 to 100 layers, many of which require this intensive calculation. To address this, ASML has partnered with NVIDIA to develop QLitho, a software library that accelerates computational lithography using graphics processing units, or GPUs. The parallel nature of lithographic simulation, calculating the diffraction of light at millions of points across the mask, is perfectly suited for GPU architecture. Benchmarks indicate that NVIDIA's Hopper architecture can accelerate these workloads by up to 40x compared to traditional CPUs. This acceleration is not just a convenience, it is an enabler. Without it, the compute cost of producing a mask for a 2nm node chip would be economically prohibitive. This integration signifies a shift where the software and hardware infrastructure for designing the process is becoming as capital-intensive as the tools used for executing it. The collaboration involves TSMC and Synopsys as well, creating a unified ecosystem where the EDA tools, the computing hardware, and the lithography hardware are all optimized in concert. Inside the scanner, the software challenge is one of determinism and real-time control. The machine manages millions of parameters, from the timing of the laser pulses, 50,000 times per second, to the synchronization of the reticle and wafer stages. The twin-scan architecture, which allows one wafer to be measured while another is exposed, requires a complex scheduler to optimize throughput. The codebase is a mix of high-level logic and low-level driver code, often written in C++ and Python. ASML has even explored the use of large language models, or LLMs, to assist in maintaining and refactoring this massive proprietary codebase. In a recent case study, they developed an evaluation framework using a metric called build at K to assess whether LLM-generated code successfully compiles and integrates within their closed, highly specialized software environment. This highlights the scale of the software engineering challenge. The machine is too complex for any single human to understand, necessitating AI assistance for maintenance. The software must also handle exception management. With a machine cost of nearly $400 million, any crash or error that damages a wafer, or worse, a mirror, is unacceptable. The code undergoes rigorous testing, including simulation in virtual environments or digital twins, before deployment. ASML cannot receive telemetry from customer machines due to IP security. Customers like Intel and TSMC do not want their yield data leaving the fab. Therefore, ASML software must be robust enough to handle any challenge without phoning home. Google Cloud is used to run massive regression tests, reducing test time from hours to minutes, enabling a culture of rapid iteration despite the constraints.
Mechatronics, the art of extreme motion. The mechanical heart of the ASML scanner is the wafer stage. It is required to move a 300mm silicon wafer with an acceleration of up to 7G in the NXE systems and 8G in the EXE systems, positioning it with an accuracy of less than a nanometer. This is equivalent to accelerating a Formula One car to 100 km per hour in fractions of a second, stopping it instantly and positioning it within the width of a single atom, thousands of times per hour. To achieve this, the stages do not use mechanical bearings, which would generate friction and particles. Instead, they float on magnetic fields. The magnetic levitation system allows for frictionless motion and fine control in all 6 degrees of freedom. The propulsion is provided by planar motors, essentially unrolled electric motors, that generate immense force with zero contact. Operating in a vacuum adds another layer of complexity. Conventional lubricants outgas in a vacuum, contaminating the optics. The entire stage assembly must be designed with materials compatible with ultra-high vacuum standards. Heat dissipation is a critical issue. In a vacuum, there is no air to carry away the heat generated by the powerful linear motors. ASML utilizes liquid cooling loops running through the floating stages, requiring flexible hoses that must not transmit vibration or exert drag forces that would disturb the positioning. Before the wafer even reaches the stage, it must be thermally conditioned.
A temperature difference of just a few millikelvins between the wafer and the stage would cause the wafer to expand or contract, ruining overlay. The wafer handler, developed by partners like VDL-ETG, uses a specialized table covered in burls, tiny ceramic pillars. The wafer rests on these burls, minimizing physical contact to prevent particle entrapment, which would cause the wafer to bulge, while water flows underneath the table to thermally stabilize the wafer. The system must condition the wafer to the millikelvin range in seconds to maintain the machine's throughput. The HNA EXE500 system introduces even more extreme requirements. Because of the 8 times magnification in the slit direction, the reticle stage must move 4 times faster than the wafer stage to synchronize the image. This requires an acceleration of 32G. At 32G, the structural integrity of the reticle stage becomes a physics problem. The stage must be incredibly stiff to avoid bending, yet incredibly light to be accelerated. This necessitates the use of advanced composite materials, likely carbon fiber reinforced polymers or silicon carbide ceramics, optimized for high specific stiffness. The clamping mechanism that holds the mask must also be robust enough to prevent the mask from slipping under these G-forces, while being gentle enough not to crush it. The global supply chain, a network of specialized dependencies. ASML is often described as a system integrator. While accurate, this term understates the symbiotic nature of its supply chain. ASML manufactures roughly 15 to 20% of the machine's components in-house. The remaining 80% comes from a network of over 5,000 suppliers. This is not a transactional supply chain. It is a collaborative development network where suppliers effectively function as divisions of the ASML enterprise. The core of the machine is built by a tripartite alliance. As detailed in the optics section, Zeiss is the sole supplier of the optical columns. The partnership is so deep that ASML holds a 24.9% stake in Zeiss SMT. The development of high-NA optics required Zeiss to build entirely new factories and excavation sites to house the massive metrology tools needed for the larger mirrors. Trumpf supplies the high-power CO2 drive lasers that generate the EUV light. These lasers are behemoths weighing over 20 tons and containing 450,000 individual parts. The laser must fire 2 pulses for every droplet of 10, a pre-pulse and a main pulse. Trumpf's recent development of a new high-energy laser is critical for increasing the source power to support the throughput of future systems. Closer to ASML's headquarters in Veldhoven, a dense ecosystem of Dutch suppliers provide critical modules. The VDL Enabling Technologies Group, VDL-ETG, is a Tier 1 partner. They manufacture the massive vacuum vessels that house the EUV source and the complex wafer handler modules. Their relationship is characterized by open innovation, where VDL engineers work alongside ASML architects from the concept phase. NTS, a global contract manufacturer providing mechatronic systems and optomechatronic modules. They develop and manufacture components for the EUV and DUV lines. Settles Savigny, a high-tech engineering firm that handles R&D and manufacturing for vacuum systems and deposition technology. They have worked on the EUV source vessel and tin management test tools. Wilvo specializes in precision sheet metal and transport tooling, while KMWE focuses on precision machining and module assembly. Shipping an EUV scanner is a logistical feat comparable to moving a small city. A standard NXE scanner requires approximately 40 freight containers. The new high-NA EXE500 is significantly larger, requiring 250 crates and 13 truckloads for transport. The total weight exceeds 150 tons. The optical modules are so sensitive that they must be shipped in active suspension containers provided by companies like Entegris. These pods protect the reticles and optics from vibration, moisture, and particles. They feature flexure suspension systems to dampen shock and purge capabilities to flush the interior with clean gas. Smart trackers from smart makers are integrated into the crates, providing real-time data on G-forces, tilt, and temperature during transit. If a crate is tilted beyond a specific angle, the warranty on the multi-million-dollar component inside might be voided. For air transport, these machines require the nose loading capabilities of Boeing 747 freighters. The shipment of the first high-NA system to Intel in Oregon was a widely publicized event, highlighting the strategic importance of these tools. The logistics extend to the last mile inside the fab. The machines are so heavy that the factory floors often need to be reinforced with specific waffle slab concrete structures to dampen vibration and support the load. The concentration of this supply chain, optics in Germany, lasers in Germany, assembly in the Netherlands, creates a single point of failure risk profile that is unique in the global economy. ASML has recognized this and is actively working to increase the sustainability and resilience of its supply chain, demanding that suppliers not only meet technical specs, but ESG, environmental, social, and governance targets. The geopolitical pressure to restrict exports to China has further complicated this network. The Dutch government's Operation Beethoven aims to keep ASML in the Netherlands by investing in regional infrastructure, but the restrictions on servicing machines already sold to Chinese customers create a complex compliance landscape. This forces ASML to navigate a web of regulations while maintaining the free flow of parts required to build these machines.
High-NA EUV, the next frontier. The current generation of EUV, 0.33 NA, is capable of printing features down to roughly 13 nanometers resolution, single exposure. To go smaller, chip makers have been using double patterning, which is slow and expensive. The solution is High-NA EUV, 0.55 NA, embodied in the TwinScan XXE platform. The XXE 5000 and the production model XXE 5200 promise a resolution of 8 nanometers. This improvement is achieved via the larger numerical aperture, which necessitated the anamorphic mirrors discussed earlier. This change ripples through the entire ecosystem. The slit field size is halved, which means the mask design must change. This has implications for the EDA, electronic design automation, software used by chip designers, who now have to account for stitching lines where the two half fields meet on the wafer. A critical component for High-NA is the pellicle, a super thin membrane that covers the mask to protect it from dust. If a particle falls on the pellicle, it is out of the focal plane and does not print. If it falls on the mask, it prints a defect. Because EUV is absorbed by everything, the pellicle must be incredibly thin, less than 20 nanometers, and transparent. However, the higher source power of High-NA systems, targeting 500 to 1,000 watts, creates immense thermal stress on the pellicle. Traditional polysilicon pellicles may melt. ASML and partners like Mitsui Chemicals and Teledyne Dalsa are developing new pellicle materials. Metal silicides, capable of withstanding higher temperatures than polysilicon. Carbon nanotubes, CNTs, the most promising candidate. CNT pellicles are incredibly strong, can be made very thin, high transmission greater than 90%, and have excellent thermal properties. ASML's research has shown CNT pellicles to be robust against the high EUV power and the hydrogen plasma environment inside the scanner. Intel was the first customer to receive the High-NA pilot system, aiming to use it for its 18A 1.8 nanometers and 14A nodes. The adoption of High-NA is a high-stakes gamble. The tools are estimated to cost between $300 and $400 million each.
The economic viability of these tools depends on their throughput. The XXE5200 is targeting 220 wafers per hour, a massive increase over early EUV tools, achieved through the faster stages and higher power sources. Intel's roadmap relies on this tool to regain process leadership from TSMC. Conclusion: the fragile miracle. The ASML ecosystem represents the pinnacle of industrial collaboration. It is a system where the flattening of a mirror in Germany allows a laser from Ditzingen to vaporize tin and Veldhoven, creating light that is guided by mathematical models computed on GPUs in California to print a transistor in a fab in Taiwan or Oregon. Key analytical insights: the shift from hardware to math. The physical limitations of optics are increasingly being solved by computation. The resolution of the machine is now as dependent on the NVIDIA GPU cluster running the ILT algorithms as it is on the Zeiss mirrors. The hardware provides the potential, the software extracts the reality. The supply chain as technology. The distinction between supplier and developer has eroded. ASML cannot exist without the tacit tribal knowledge embedded in the workforces of Zeiss, Trumpf, and VDL. This makes the technology extremely difficult to replicate. A competitor would not just need to steal the blueprints, but to replicate the organizational culture and intercompany trust of the entire European high-tech value chain. The thermal limit. As power scales, heat management is becoming the primary bottleneck. From the pellicle to the wafer stage, the battle is for thermal stability. The engineering has moved from preventing heat to managing heat with millikelvin precision. In summary, ASML's lithography machines are not just tools for making chips, they are the physical manifestation of a global industrial capability that balances on the razor's edge of physics. The successful deployment of high-NA EUV will likely dictate the pace of technological progress for the next decade, determining the feasibility of AI, high-performance computing, and the next generation of consumer electronics.